Hello, welcome back. So we were discussing about the lacing system. So in the previous part, I have discussed about the general requirement of the lacing system. So now in this part, we are going to discuss about the design specification. What are the various specifications that we follow as per this clause? So first I will show you this clause and I will show you all the paragraph that we are going to follow in our slide. So first I will be showing you this clause. So here you can see in the IS code, this is the clause number 7.6. So the whole clause we will be following. So 7.6.1 is about the general specification I have already discussed. So all these paragraphs we will be following. So one by one, I will be explaining all these paragraphs in the slide, but I am showing you here that all the values I have taken from this IS code from this clause. So the diagram also you can see I have used the same diagram in my slide, and there you can see the close width of lacing bar, then thickness of lacing bar, what will be the angle of inclination, spacing, all these values I have taken from the IS code. So all these values you can find out from here. So this is what I am doing just to show you that how and from where I have found all the value. So all this close, so up to, so there the next close starts 7.7. So up to 7.6.8, all the close we will be following one by one. So I will be showing you all in the slide. So here now we will discuss about the design specification. So in the design specification, the first point that we have to find out is force in the lacing bar. Like you can see, this is the main component, and to join these main component we are providing this lacing bar. So there must be some force in this lacing bar also. So how much that force is, we have to see that. So here it says lacing bar, the lacing of compression member shall be proportion to resist a total transverse shear, which is V value, at any point in the length of the member equal to at least 2.5% of the axial force in the member, which shear shall be considered as divided equally among all transverse lacing system in parallel piling. So I will explain this process, what they are saying. Basically, we have to understand, see, these are the two components that we have to connect with the lacing system. So whenever, so these two components actually supports this main load. Say this is the P. I am writing this. So this is the main load which this component is going to support. So when this load will come, these two members will try to get away like this. So to hold them, what we do is we provide this inclined member, which are the lacing. So you can see here, this is the force that is happening because of this P value. So this force is called the V value. So to resist this V value, we are providing the lacing bar. So basically, this is the shear. This V value we call transverse shear. Transverse shear. So in the IS code, it is being mentioned that the value of this V is equals V is equals to 2.5% of P, which is this one. So P value will be given already in the question. So 2.5% of P is V. So now, as you can see, this lacing bar will be resisting this transverse shear. So because of this transverse shear, the force in the lacing bar will be along the length of the lacing bar. So you can see lacing bar is inclined, so force will be inclined also. So we have to find out that inclined force, what will be the value. So that F value, I'm writing that force as F. So that F value is dependent on the value of phi. I will show you how. So I hope now it is clear to you what is V value. And V value is taken as 2.5%, which is mentioned here. So there you can see it is mentioned here. So this is what they are saying in this paragraph. So I hope now you understand. We will now move forward. So therefore it says the total shear force will be 2.5% of the P value, and P I have just discussed. This is the axial load the built up member are going to support. So now we are going to see what is F. In the diagram now you see, as I said, that these are the inclined member, and in the inclined member this V is the shear force, and as the lacing bar is provided on both sides, on this side, on face A and on the face B also. So that is why the shear force which the lacing bar is going to support, it is actually distributed in two faces. So on one face it will be half of the shear force. So the V value that we have calculated, which is 2.5% of P, on single lacing, on this lacing, it will be calculated as F value, and F value is basically calculated from the V value, this V value. So there you can see, if I write here as, just writing the force diagram, I'm just making the force diagram. So this horizontal force is V value, and this this V has another component, but our lacing bar is like this, and force is also in this direction along the lacing bar. So we are supposed to find out this F value, how much force will be there in the lacing bar. If the angle between the lacing bar and the vertical component is theta, then we have to find out this F in terms of V. So I hope you know how do we resolve the force. So ultimately, if I write F is equals to F sine theta. So if this is the F, its horizontal component will be this one, and this one will be the F sine theta, while the value of this component is already given, which is V. So if I equate F sine theta with V value, then we can easily find out F as V upon sine theta. So as I'm talking about the one single lacing bar, so on the other face, it will be having the same. So this face is having V by N, which means I'm writing here as 2. So on single face, it will be half of V. On the other face, it will be half. So that is why here it becomes V by 2. So I'm writing here V by 2 sine theta. So F value will become like this. So this is the force in one lacing bar. In one lacing bar, force in will be V by 2 sine theta. So this is how we are calculating, and this is how we calculate the value. So N is the number of phase. How many number of phase you have provided the lacing system. So generally we provide on two phase. If we are providing on the two phase, then it will be phase A, and on the opposite side phase B. So because of that, V will be divided into two. Similarly, in case of double lacing bar, there you can see, so in a single spacing, which is L value, so in the single spacing, you can see one lacing bar is there and one lacing bar is there. So in that case, there are two lacing bar, and on the other face also there will be two lacing bar. So in that case, N will become 4. While in this case, N will become 2. So that is why I have divided V by 2. But in this case, it will be V by 4. So in that case, F value will become V by 4 sine theta. So this is how we calculate the force in the lacing bar. So in this case, in the double lacing system, what happens is one lacing bar is in tension and the other lacing bar is in compression. So this is the phenomena that occur in double lacing system, while in this case all the lacing bar are in compression. So that is why. So there you can see force in double lacing system is lower than the force in single lacing system. It is 1/4 of V, while it is half of V. So that is why single lacing system is more critical than the double lacing system, and that is why they are more efficient. So I have written here. So in the single lacing system, it will be V by 2 sine theta, and N is the number of transverse system plane. For double lacing, it will be V by 4. So I hope it is clear how it arrives here. So as I said, the force will be tensile in one lacing bar and compressing in the other. It will occur, this phenomena will occur in double lacing system. So in this, one lacing bar will be in tension and the other lacing bar will be in the compression. Now talking about the slenderness ratio. So now just see, these are the two main component and they have their own lambda. I mean they have their own length. Say I'm writing here as L. And similarly, now you can see to connect them, we are providing the lacing system, lacing bars. So this single lacing bar, this is also act as a strut. And it will also have its own lambda value, which means it will be based on this value. So they have their own length also. So that is whenever we are designing the lacing system, we also find out the lambda value to check the slenderness ratio against the limit. So slenderness ratio limit is given here, and as per IS code, it says that the lambda value should not exceed 145. So it says here that the slenderness ratio, which is the ratio of LE by R, LE is the length of lacing bar of one lacing bar, and R is the minimum radius of gyration of the lacing bar. Okay, so this ratio should not exceed 145, and this limit is given in table 3 of IS code, so you can check that. And also the value of effective length in the lacing bar can be calculated as per IS code instructions recommendations. So in this case it says when there is a single lacing, in that case effective length of lacing bar will be equals to the actual length of lacing bar. I am again talking about this length, this one. This is the actual length and LE is the effective length. So in this case LE will be L. Similarly, if there are double lacing system, in that case effective length will be equals to 0.7 times of L. If there are welding, I mean if the lacing system, lacing bars are connected using the welded connections, in that case effective length will be equals to again 0.7 times of L. So how do we find out effective length? So this is the process that is being given in the IS code. So I have made this table. So in the lacing system, as I said, that generally we use flat bars. So flat bars is having thickness and width. So lacing bar looks like this. Lacing bars are basically the flats. So they look like this. And this one is called the B value, and this one is called the T value, which is the thickness of the lacing bar, and B is the width of basic lacing bar. So basically, how do we find out the lambda value? Lambda value is LE upon R. Now R is the radius of gyration. In the bar, you can see there is one axis, this one, and this one is the another axis. So this axis is say this is the say Z axis, and this one is the Y axis. Okay, so in this case, how do we find out the how do we find out the minimum radius of gyration? So minimum radius of gyration will occur along this axis. So along this axis, I'm writing here directly. So as I know, R will be equals to under root I by A. Now I is the moment of inertia. Moment of inertia, if I find out about ZZ axis, it will be BTQ by 12. See, we already know how do we find out moment of inertia about the centroidal axis. So BTQ by 12 will be the I value, and A will be B into T. So putting this value, this becomes BTQ by 12 upon BT, and solving it, so ultimately it becomes lambda value becomes LE under root multiplied by 12 upon T. So T is the thickness of lacing bar and LE is the effective length of bar. So ultimately what I have done is by this derivation, I have arrived at this formula to calculate the lambda value of the lacing bar, which is LE under root 12 upon T. So from this formula, I will be able to find out the value of lambda directly. So this value should be less than 145. If it is less than 145, then we say that lacing bar will be safe. Now, width of lacing bar. So this B value, how do we design this B value for the lacing bar? So in the IS code, in this clause, IS code has given some recommendation about the width of lacing bar. So IS code recommend that the minimum width of lacing bar should be more than the 3 times the nominal diameter of the end bolt. So whatever bolt we are using, if we are using the bolted connections and if we are using the bolt, so bolt dia may be D, so the width of lacing bar should be more than 3 times of dia of the nominal, dia of the bolt. Similarly, how do we find out the thickness? Thickness provision is also given in the IS code, but that we will discuss in the next part. Thank you.